A vehicle travels down a city street at 60 kilometers per hour. An e-scooter crosses the lane. The autonomous emergency braking system registers the trajectory and slams the brakes, dropping the speed to 30 kilometers per hour. Traditional functional safety standards, like ISO 26262 and SOTIF, assume a system's operational boundaries are static. Engineers test hardware for faults and verify software limits before deployment, treating the operating environment as a fixed, fully verifiable equation. Autonomous systems driven by machine learning operate differently. These neural networks produce probabilistic outputs. They process pixel arrays to calculate the statistical likelihood of an object's identity and future path. The black box nature of AI means engineers cannot manually map every conceivable input to an exact output. Because the mathematical logic is opaque, identifying every potential hazard before the vehicle reaches the road is an impossible task. In December 2024, the automotive industry addressed this limitation by releasing the ISO PAS 8800 standard. This standard introduces continuous assurance. It replaces the idea of a final pre-deployment sign-off with an active post-deployment safety lifecycle. Manufacturers must monitor the vehicle and update the safety evidence as long as the fleet remains operational. For autonomous AI, safety is a dynamic architectural process designed to manage residual risks in an open-world environment. ISO PAS 8800 classifies residual risk into three sources: initial development uncertainty, inadequate maintenance, and the evolution of the operating environment. Safety arguments rely on operational assumptions. These are strict definitions of the environment established during development. If real-world conditions deviate from these definitions, the safety case becomes invalid. This 3D distribution curve maps the original training parameters for our braking system. The dataset assumes pedestrians have standard human silhouettes and move at walking or running speeds. The environment evolved as urban centers saw a massive increase in e-scooters. These riders present a unique vertical silhouette and move at 25 kilometers per hour, faster than a runner, but slower than a car. This deviation is known technically as distributional shift and concept drift. The environment has introduced out-of-distribution, or OOD, data that the neural network was not designed to handle. When AI processes OOD data, the model often exhibits overconfidence. It predicts an outcome without triggering an internal error state, meaning the system fails without realizing it. The emergence of the e-scooter represents a broken assumption. The environment has changed so significantly that the vehicle's original safety argument no longer holds. Since neural networks can be overconfident in their errors, the primary AI model cannot be trusted to monitor its own performance accurately. ISO PAS 8800 Clause 14.6 requires technical and non-technical defenses, specifically an independent runtime monitoring module. This block diagram shows the standard perception flow. Raw sensor data feeds into the primary vision AI, which sends driving commands to the vehicle control module. Clause 14.6 establishes a parallel architecture. A duplicate stream of sensor data routes into a runtime monitor that operates entirely independently of the primary AI's logic. The monitor uses statistical mechanisms like Gaussian mixture models or variational autoencoders. It checks the signature of incoming data against the original training distribution. When it encounters e-scooter data, it flags it as a high-risk anomaly. These flagged samples generate safety performance indicators. The monitor calculates an uncertainty score, triggering a system-level warning while transmitting the anomaly data to fleet operations for analysis. These technical monitors are paired with non-technical defenses, such as HMI designs that manage reasonably foreseeable misuse. This ensures the driver understands the system's limits. Under Clause 14.6, the vehicle functions as an active investigator of its own environmental boundaries, rather than a passive executor of code. Collecting new field data, retraining the neural network, and validating the update takes weeks or months. This timeline shows the gap between detecting a broken assumption and deploying a software fix. This period is the safety vacuum. Operating a vehicle under a known broken assumption during this vacuum is an unacceptable risk. The standard requires immediate runtime risk mitigation to offset the identified residual risk until the software can be updated. This matrix shows the two paths for mitigation. The first is to restrict the operational design domain. By preventing the vehicle from entering the scenarios where the AI fails, you reduce the probability of an accident. For example, if glare is the identified trigger, the system might restrict autonomous features during specific sun angles. The second path is graceful degradation, which limits functionality to lower the severity of a potential failure. In our e-scooter case, the manufacturer applies a geofence around university campuses. Inside these zones, the system forcefully limits the maximum autonomous speed from 60 to 30 kilometers per hour. Reducing the speed by half changes the collision physics. It cuts the kinetic energy and doubles the reaction time. This mathematically offsets the AI's degraded perception confidence. Over-the-air updates are not a complete safety solution on their own. Runtime degradation is the necessary engineering response to survive the safety vacuum. A safety assurance argument is a logical web of evidence proving the vehicle is fit for the road. This network graph represents that safety case. When the e-scooter event occurred, the nodes asserting safety for urban pedestrian recognition were invalidated. Clause 11 of ISO PAS 8800 dictates that new field data must follow a data V model, rather than being dumped directly into a training server. E-scooter imagery becomes a safety artifact. Engineers ensure strict traceability, matching field data sensor resolution and noise profiles to production cameras. After retraining and validation, the new model is pushed to the fleet. Once the AI accurately classifies e-scooters, the software update is deployed. With the safety assurance argument fully restored, the vehicle automatically lifts the 30 km/h limit and safely returns to full autonomous functionality. Safety engineers monitor this life cycle using tools that link fleet performance indicators directly to the safety argument. ISO PAS 8800 provides the engineering blueprint required to extract predictable safety from an unpredictable environment.